Hello, it is October 6th, 2 o'clock, and this is Homework 1, Part 1. We are going to be looking at a sealed cylindrical tank with height h, which is going to be 1 meter. Height of the full tank, so h is equal to 1 meter. Cross-sectional area, 1 meter squared. That is cross-sectional area of the tank. The tank is filled to initial height of 0.9 meters. So H initial of the water is 0.9 meters. Go ahead and draw that in real quick. This is H initial. The headspace above the water is initially standard atmospheric pressure, which is 101.325 pascals. A hole the size of 0.001 meters squared is punctured at the bottom of the tank and water drains out at an unknown velocity. So that is our hole and our water draining out at a flow rate that we do not know yet. And what we need to do is we need to derive a differential equation for solving the height of the water in the tank as a function of time. And then once we do that, once we derive that, we're going to solve it numerically in collaboratory. So let's define a couple other variables here. We need to know what h is. H is the height in the tank as a function of is time. H is the height of the tank at any given time. So as the water level decreases, h will be the height of the tank. So height of the water at any given time. What else should we note here? I think that is all for now. So the strategy for doing this is we're going to take the volumetric flow rate equation and use Bernoulli's equation to solve for the velocity, and then plug that into our volumetric flow rate equation and derive that in terms of height with respect to time. So we can start, sorry about the sirens. We can start by looking at the volumetric flow rate equation, which is the flow rate out is equal to the velocity of the liquid leaving times the area of the hole, the cross-sectional area of the hole. Oh, that's one more thing I didn't mention. Or I did, I just haven't written it down. The area of the hole we said was 0.001 meters squared. So area of the hole. We can rewrite this in terms of height of the level of the water on the inside. Is we can write that as the cross-sectional area times the height with respect to time would be equal to the negative flow rate out. We can then plug in what we know flow rate is equal is. We can plug this into our flow rate. That's what I was trying to say there. And we would spit out the cross-sectional area of the tank times the height with respect to time would be equal to the negative area of the hole times the velocity of the water leaving the hole. If we then divide the cross-sectional area out, we then are left with an equation that is solving the height of the water in tank as a function of time. That is just what we need. Now, our givens for the equation, we know the area of the hole and the cross-sectional area, but we do not know the velocity of the liquid leaving the tank. So we need to solve for this now. We have our equation. We just need to solve for the velocity of the liquid leaving the tank. And we can do that using Bernoulli's equation, which I've already written down. We know from Bernoulli's equation the givens that we can plug into here. Let me rewrite it so it's easier. Bernoulli's equation is P2 minus P1 over the density, rho, plus velocity 2 squared minus velocity 1 squared over 2, plus g z2 minus z1 is equal to the negative heating coefficient. We are assuming this is 0 for this problem. We are also assuming, since the velocity inside of the tank, the water, there's enough water and it is large enough that we can also assume that is 0. We can substitute the change in the z value as just our height, our value h, which is the height at any given time. Since the height is going down, this constant is going to be negative. The pressure outside of the tank, since it is atmosphere, is always going to be 101,325 pascals. And we know we are solving for the volume or the velocity outside of the tank. So that is what we want to solve. Now let's rewrite this with what we have, which is 101,325 minus P1 over rho. Come on. Plus V2 squared over 2 minus GH is equal to 0. We can solve for P1, which is the pressure inside of the tank, using our Perv-Nernst equation. So N is equal to PV over RT. For the outside of the tank, we know that 101,325, that's the pressure. The volume would be the cross-sectional area times the height, or this is for not the outside, this is for the initial case, minus height initial would be over R times T. So that is what N is equal to. Since this is a closed system, N is always the same. So when we need to solve for P1 is equal to nRT over V, we can plug in N again. Minus H initial over RT. Times RT over the changing volume, which would be AC, a cross-sectional area, times the height of the tank minus the height with respect to time, or the height at any given time, as the water level moves. We can then see things cancel, RT cancels, AC cancels, which leaves us with P1 is equal to 101,325 times H minus H initial over third time's a charm. There we go. Over H minus the height at any given time. So then we can plug that back into our equation, which gives us 101,325 minus 101,325 times height minus height initial of the water over, why can't I ever do that, over height minus height at any given time. All of that is over rho, density of the water, plus V2 squared over 2 minus G of H equal to 0. Now we know that we need to solve for V2, so we could pull that out by itself. Which would be equal to G of H plus, and then we can break this up a little bit. So we're left with 1 over rho. That is going to be times 101,325, and then if we distribute this, brackets H minus H initial over H minus H as it changes, and then this will be minus 1 because we have this coefficient here. Back that off. Then we can divide both sides by 2 and square root to leave V2 by itself. So velocity on the outside of the tank would be equal to the square root 2 times everything inside, which is GH plus 1 over the density, multiplied by 101,325 minus H initial over H minus 1. Close that. And that is what we needed to know. That is the, that is the velocity on the outside of the tank, which is what we needed to know for our height with respect to time equation. So now when we plug in V2, we can solve the height with respect to time. Now I'm not going to do that right now because it'll be gross and funky. So we can do that when we plug all of this into Colaboratory. Thank you very much.